All right, so welcome to the lecture on skeletal physiology. We're going to be talking about the growth, the physiological activity, and the healing of skeletal tissues. First, let's talk about what the general functions of the skeleton are, and then we can get into how those those functions are physiologically accomplished. So, physical, the skeleton is a hard collection of bones that both support the weight of our body and protect our soft organs. Okay, you can think of many of the bones in your body very obviously have a support function, but you also can think about how the sternum and the ribs protect your heart and lungs. The cranium protects your brain. Together with the skeletal muscles, another physical activity that the skeleton supports is movement. Think about what disaster would occur if the skeletal muscles tried to contract and there was no skeleton to pull on. You would just flop your entire body into very strange shapes. Physiologically, then, more homeostatically, I should say, stem cells in the red bone marrow give rise to all of the cells that circulate in your blood, and that process gets its name from the Greek word for blood, heme, and the Greek word for formation of something, poiesis. And so we put those together to make hemopoiesis, which is a funny word, but it works. The other two major functions that the other two homeostatic functions that the bones perform for us is that they store minerals and they store energy. Calcium phosphate crystals that make up the hard part of your bone are a great place for the body to store calcium and phosphate as well, two minerals that are important for our body's function. Adipose tissue found in the yellow bone marrow plays an essential role in storing a little bit of excess energy, though really your body tends to look to that energy storage last. I mean, you would much rather take fat out of your abdominal fat or other fat storage areas than out of the yellow bone marrow. Calcium. We're all told as we grow up that we need to drink milk, we need to have calcium in our diet so that we have strong bones. But in fact, we also need calcium for a number of other things that our body relies on, and the bones help us manage how much calcium we have. For example, both cardiac and smooth muscle tissues need calcium from the blood to contract in the first place. Also, blood clotting factors require calcium to be able to stop you from bleeding, what we call hemostasis. If we have too much calcium in our blood, we need to get rid of it. How can we do that? Well, we can throw it away in the urine primarily, and also a little bit in the sweat, but that's not very efficient of us. What if we need that calcium later? So we can store the calcium away for later by building a little bit of extra bone tissue. That's a much better solution. What if we have too little calcium in our blood? Where can we get some more? Well, we can always absorb calcium from our digestive tract, which is a good solution because it gets new calcium into our body, but it only works if we recently ate some high calcium food. Or if we don't have high calcium food in our digestive tract right now to pull much calcium in, we can take apart a bit of that extra bone that we built just a few lines ago when there was too much calcium. Okay? So what happens if the calcium levels in our blood are off a little bit? We just talked about some of the things that respond in our body, the urine and the digestive tract, but let's talk about the bone response specifically. If the blood calcium levels are too high, the thyroid gland releases a hormone called calcitonin. Okay? Calcitonin instructs osteoblasts, remember those are the blasts are builder cells, osteoblasts to start secreting new bone tissue. As that new bone tissue is made, calcium is removed from the blood to be stored in the new bone tissue. When we remove tissue from blood that's too high in calcium, or when we remove calcium from blood that is too high in calcium, that brings the blood calcium back to normal. What about if the blood calcium levels are too low? This is actually much more critical for us. We can't contract the muscles of our body, we can't send nerve signals, we can't clot our blood if we don't have enough calcium. So the parathyroid glands release a hormone called PTH, which stands for parathyroid hormone, very creative name there. And the parathyroid hormone tells osteoclasts to step up their game. And remember, osteoclasts are the take-apart cells. Osteoclasts start resorbing or dissolving away bone tissue. Calcium from that resorbed bone tissue is then added to the blood, and when you add calcium to blood that's too low in calcium, that brings the blood calcium back to normal. You may have figured out already that these are both what we call negative feedback loops, in that by the time you finish the process, you've reversed the change that was causing the problem in the first place. Okay, now we're going to move on to talking about how bone tissues, how skeletal tissues rather, grow. So before we get to the bone tissue, which is a bit more complicated, we're going to talk about how cartilage grows. So there are two ways for cartilage to grow. You can grow, there's interstitial growth, which is growth from within the tissue, okay? And we refer to this in several different tissues, not just cartilage, that can have interstitial growth, growth from inside. The opposite of that is appositional. Appositional growth is growth from the edge of a tissue. There is also interstitial and appositional growth of bone that we'll get to in a little bit. So how cartilage grows and how cartilage forms in the womb are basically the same thing, because cartilage does not grow very much in adults. In fact, it doesn't grow at all in adults. It doesn't grow very much in children. So the initial formation of cartilage from chondroblasts and the enlargement of the cartilage as the baby, the child grows, are about the same process. What happens is, if you have a little bit of cartilage already, you're going to have some chondrocytes inside the matrix, inside the ground substance of the tissue. So those chondrocytes are going to divide to become chondroblasts. Now, as you know, a blast cell is a builder cell, so chondroblasts are going to build new tissue. They're going to surround themselves with new matrix. But then the odd thing happens that once they're fully surrounded by new matrix, they become chondrocytes again. And what you have done is taken one chondrocyte, turned it into two chondroblasts, surrounded each of those chondroblasts with new tissue, and you've ended up with two chondrocytes surrounded with tissue again. So what about appositional growth then? This is how cartilage forms in the first place, and it's how cartilage enlarges on the outside of the tissue. So instead of having chondrocytes already in the perichondrium, you actually have some stem cells there, some cartilage stem cells. And those cells divide to become chondroblasts. Now, as you know, chondroblasts are builder cells, so the chondroblasts are going to form a layer of new matrix around themselves. In this case, they're going to form the new matrix at the edge of the tissue. Then, once they have surrounded themselves fully with new tissue, the same thing happens as if you were doing interstitial growth. The chondroblasts become chondrocytes. So the difference between interstitial growth and appositional growth is not the last part, the forming of new matrix and the forming of new chondrocytes. It's where the chondroblasts come from. In interstitial cells, you have a chondrocyte that decides to turn into a chondroblast and grow some new tissue around it. In appositional growth, you have stem cells that are constantly forming new chondroblasts, and those chondroblasts surround themselves with matrix and become chondrocytes. Okay, so cartilage growth is fairly simple. What about bone growth? Well, there are two kinds of bone growth. There's the formation of new bone, which happens in utero, and in some cases in the early stages of neonatal development, early childhood. But then there's growth of bone, which is the enlargement of bone throughout the child's life. And we'll talk about these in two different stages. Things that form new bone in the womb are called ossification, because you start with tissue that isn't bone and you ossify it. You make it into new bone. And there are two kinds of ossification. There's intramembranous ossification. You can parse that, the ancient Greek words there, intra meaning inside, membranous meaning a membrane. So the first kind of bone we're going to talk about is inside a membrane. The bone originally forms as a membrane of tissue, and we're going to form a bone inside that membrane. So what happens is that the ossification centers form within this thickened membrane, also known as mesenchyme. The osteoblasts do what osteoblasts do. They form new bone tissue called osteoid around them. As that osteoid starts to gather calcium, it forms osteoblast cells, which each have little canaliculi forming outside to communicate to their neighbors. But these are going to stay trapped in that calcified matrix until they are, for the rest of the life of that bone, as maintenance cells. And so this place where you have osteoid being secreted on the outside and calcification happening on the inside is called an ossification center. So one of the things that distinguishes intramembranous ossification is that these ossification centers don't happen in just one place. They're scattered throughout the membrane. And as the bone grows, you have bits of calcified bone with osteocytes trapped in it that just grow together spontaneously from randomly different directions. And the bone type that's formed there is called woven bone. So ossification centers form, they come together to make woven bone. And then over time, that woven bone gets reshaped into lamellae. The parallel lamellae of the trabecular or spongy bone and the concentric lamellae of the compact bone on the outside, but in either case it's referred to as lamellar bone, which is mature child and adult bone tissue. And this all happens entirely in utero. So by the time the baby is born, these flat bones that form from intramembranous ossification have entirely formed the two tables of compact bone and the diploe of spongy bone in the middle. Also worth noting is that there is some part of this membrane that the bone is forming in that does not form bone. Well, what's that going to be? It's going to be the membrane outside the bone, and we know the name for that is the periosteum. So these pink regions that stay outside the bone become the periosteum on the outside and the inside of the, the top side and the bottom side or whatever of the flat bone. If you look at my online PowerPoint, there's a step-by-step process here for you to fill in the blanks. I think the blanks will be fairly obvious if you look at what we just talked about, that bone begins as a membrane, then what kind of cells would secrete osteoid, creating ossification centers. Those centers begin to calcify, and cells now turn into what? The mature maintenance cells. Centers grow outward and form the woven bone, and layers of the membrane outside of the bone become the what? Periosteum, right? And then the woven bone turns into, we just said this was lamellar bone, and then it asks you to figure out the outer regions become what bone tissue type, and the inner region becomes what bone tissue type. So there's another kind of bone in our body, though. There are the flat bones, but there are also the long bones of our skeleton. These are not flat membranes of bone, so it doesn't make sense for them to form from a flat membrane of tissue. So what it does make sense is for our body to make a template. And we make the template originally in utero out of hyaline cartilage, which is a sturdy enough shape that it can hold a sturdy enough tissue that can hold your body shape and maybe even bear a little bit of weight while your body starts to then ossify the cartilage. And so since you're ossifying from the inside of a cartilage, it's called endochondral ossification. So what happens is that between 8 to 12 weeks in the embryo stage, the body forms a rough skeleton of cartilage. Then in almost all vertebrate mammals, the exception being sharks and rays, their cartilage remains cartilage, their skeleton remains cartilage their whole lives. But for most of us, from fishes up to humans, there begins a process of turning that cartilage into bone. And so what happens is that osteocytes inside the middle of the diaphysis start to take apart the cartilage matrix and replace it with new bone, with osteoid. Okay, that osteoid then starts calcifying, just as it did in the intramembranous ossification, and so we get an ossification center. And this is called the primary ossification center because it's the first place in the bone where ossification, bone forming, starts to happen. Again, we get the woven bone that becomes spongy bone on the inside and the woven bone that becomes compact bone in the cortex of the bone, in the long shaft. And eventually blood vessels reach into the inside of the bone, which cartilage, you remember, doesn't have any blood supply, but bone does. So eventually blood vessels reach into the bone to supply the growing bone. By 16 weeks in fetal development, you can clearly see that there is bone tissue forming in the long parts, in the diaphyses of the bones. But if you look at the skeleton of a neonate, there is plenty of cartilage on the outside of the bones. At that point, somewhere near newborn age, the secondary ossification centers form. These are called secondary because they happen after the primary ossification center has finished its job. So again, new blood vessels form into the cartilage. Osteoblast cells start taking apart the cartilage matrix and replacing it with new osteoid, new bone matrix. Ossification centers form and start replacing the osteoid with woven bone, calcified woven bone, and eventually we end up with that same structure, the woven bone on the inside, or the spongy bone on the inside, the compact bone all the way around the outside of the bone. Just as that is starting, the osteoclasts inside the marrow cavity are starting to take apart the medulla of the bone and form a medullary cavity out of what was a spongy bone area there in the middle of the bone. Then again, if you download the online PowerPoints that go along with this lecture, you can practice filling in these blanks. What kind of tissue is the bone template made of? Which physis, is it the diaphysis or the epiphysis that begins to ossify first? We have which type of cell, osteoclasts or osteoblasts, are going to secrete, or osteocytes, are going to secrete the osteoid to form a periosteal bone collar there. Then a primary ossification center forms, and blood vessels invade, and osteoblasts invade the core of the bone shaft, and bone develops in both directions from the center. Then a secondary ossification center, well, several secondary ossification centers form in the what? The diaphysis or the epiphysis from birth through early childhood. And finally, between those two, and this is the key to the next thing we're going to talk about, between the two, between the epiphysis and the diaphysis, there remains a plate of cartilage called the epiphyseal plate. And that is where the bone is going to grow in length. If you imagine that this bone here, this bit of the radius here, grew, the primary ossification center grew up this way until it reached the end of the diaphysis, and the secondary ossification center filled in the epiphysis here, but they left a plate of hyaline cartilage between the two. Same thing happened here in the ulna. And you can see in this radiograph here that there's a faint line, almost looks like somebody broke the end of every single bone. No, those growth plates, or epiphyseal plates as they're properly called, are naturally there, and that's what allows the bone to get longer and longer and longer as the child grows. If we zoom in on those little plates of cartilage, we see this really remarkable structure that proceeds from the epiphyseal side here to the diaphyseal side here. Okay, so this is where the epiphysis would be. This is where the shaft, the diaphysis, would be. And the bone grows from the inside of that plate. So out here, most of the cartilage in the plate is just resting cartilage. It's just there to kind of hold the shape of the bone and bear some weight. Under that, or closer to the middle of the bone, is proliferating cartilage. That's where you've got lots of those chondroblasts that are busy building new cartilage over and over and over again. So this cartilage looks kind of stacked into plates. Then the cartilage stops actively proliferating and starts filling itself out, and that's called hypertrophy, large growth. And so this is hypertrophic cartilage. And then a funny thing happens. The cartilage kind of commits suicide. It starts to calcify. And calcified cartilage is dead cartilage. So these cells are really, quite literally taking one for the team. They're committing suicide by filling themselves with calcium. And then once they have created a calcified zone, the osteoblast cells can come in and start rebuilding. Osteoclast and blast cells can start rebuilding that by creating zone 5 is an ossification center. It's a zone of ossification. And one last explanatory note is that as this gets ossified, then the ossification center moves up, and the calcification center moves up, and the hypertrophic zone moves up, and the proliferating zone moves up. And so that's how you add length to the bone, is you keep pushing the resting cartilage up and replacing it from the bottom with more and more bone. And so this is the end of that same figure we were looking at with the bone growth, the endochondral ossification in the first place. And this shows what the late childhood bone looks like. It's got that epiphyseal plate with the various zones of cartilage, resting cartilage here, and then proliferating, hypertrophic, calcified, and then you can see the ossification zone there. And so that's constantly pushing out on the epiphysis to make more diaphysis. So you're making the bone longer, but maintaining more or less the shape of each epiphysis. And so that is basically going to stretch out all of these bones as the child grows. Then, when the child becomes an adult, that epiphyseal plate is no longer needed, and so you stop making new cartilage, and all of the cartilage that's there ossifies. And what's left, all that's left of it, is a single line of compact bone that goes across between diaphysis and epiphysis, or kind of goes through the epiphysis, I guess. And it's called the epiphyseal line at that point. So in a child, it's an epiphyseal plate because it's actively growing. In an adult, it's just this remnant line called the epiphyseal line. But you might say to yourself, wait a minute, I know that a child's bones have to grow in length, but don't they also have to grow in width a little bit because the kid gets heavier, and so you need a sturdier bone to hold that weight. So it's true that bones also grow in appositional growth. They also get wider. And so osteoblasts in the periosteum, so that's out in this region here, are going to secrete new circumferential lamellae of bone matrix, and that's going to make the bone thicker. At the same time, osteoclasts from the endosteum, that's in here, are going to start resorbing, dissolving and removing older bone that's no longer needed from the inside, and that keeps your bone from getting too heavy as it gets wider. And so that then gets replaced again, and as the bone gets bigger, you get more new growth here on the outside, and you get more old bone resorption on the inside, and eventually you get to the size of an adult bone that is still, it's gotten a little bit thicker in actually, how thick the actual compact bone is, but the bone itself is much, much wider than the infant bone, and that's because the osteoblasts add layer after layer after layer of new bone out here, and the osteoclasts slowly take apart the inner layers to keep the bone from getting too heavy. Okay, just two more points then. Remodeling. Bone is, as I've said a couple of times in this lecture, it's a living tissue. It's got blood vessels in it, it's got nerves in it, it's got actively working cells in it. But bone crystal itself is not really a living thing. You know, it's a calcium phosphate crystal. It's not a whole lot different than chalkboard chalk, which is calcium carbonate, but it's a similar idea. So every now and then, the bone the bone matrix gets little tiny hairline cracks in it. It gets microfractures. It gets things that it takes some damage as you walk on it, move it, slam it into things. To keep any of those little cracks from becoming major big cracks, your bone is constantly taking apart the old bone tissue and replacing it with new bone tissue. So the bone matrix that you have today is not the same bone matrix you had 10 years ago. The bone matrix is constantly being resorbed and redeposited. And the really nifty thing is it gets taken apart and put back in, it gets taken apart from the, mostly from the places where the bone is not bearing any weight, and then added preferentially to the places where the bone is bearing weight. So your bone gets thicker where it's needed and thinner where it's not. 5 to 7%, some little facts here, 5 to 7% of your bone mass is recycled every single week. Spongy bone gets completely replaced, taken apart and put back together every 3 to 4 years. The compact bone on the outside of your bones is replaced about every 10 years. So very literally, the bone you have in your body now is not the same bone you had 10 years ago. This allows the body to prevent the calcium from getting too brittle. It helps with that buffering of calcium in the blood. And most important, it allows the body to respond to mechanical stress by adding more bone where it's needed, and yet lighten the bones by taking away bone where it's not needed. Interesting side note, since we live in Houston, or in the Houston area, one of the important things in maintaining the health of astronauts on space flights and the space station is that problem that bone will go away where it's not bearing weight. Well, what's the problem in space? No weight. You're weightless. So they have to develop innovative exercise programs to try to keep putting weight on those bones in an artificial manner to convince the bone that it's still needed. Otherwise, your bones will start losing bone mass while you're in space, and when you come back down to Earth, boy, is that going to not be a good situation. This time, this is the one place in the body here where the osteoblasts and osteoclasts, so the osteoblast cells and osteoclast cells work in remodeling units, and they work together to remove the old bone. The osteoclast goes in front and removes the old bone. The osteoblast comes in behind and puts in fresh new bone. And the cells that stay in the tissue, the osteocytes, the maintenance cells, have stress sensors. They can tell when the bone around them is being compressed or stressed, and they inform the remodeling units around them, the osteoblast, osteoclast teams, where the bone needs to be added and where the bone is allowed to be removed. Finally, last but certainly not least, integrating a lot of these concepts into a why do I care clinical framework is the idea of how broken bones heal. Okay? First off, it's very similar to how long bones form in the first place. Okay? The first step is to form a cartilage soft callus to hold the shape of the bone. Then a bony hard callus replaces that so that the bone can once again hold weight. Once the bone callus is in place, then we call back the remodeling that we just talked about, and the bone callus is slowly hollowed out where it's not getting stressed and strengthened where it is getting stressed, and eventually takes on the shape of a shape very close to what the original bone looked like once the patient starts putting stress on that bone again and using it the way it's supposed to be used. So the steps are, first you break the bone, and when you break the bone, you break a lot of blood vessels. So a structure called a fracture hematoma forms. The periosteum is swelled outward by blood that it's capturing inside the bone, and then the bone swells. So one of the big signs of a broken bone is not only that it's tender and painful and you can't put weight on it, but that it gets very swollen. Then the fibrocartilaginous soft callus forms. Okay, we're using fibrocartilage here instead of soft cartilage, instead of hyaline cartilage, to be sure we can hold the shape of that bone and make it bear weight if it needs to. Then once that fibrocartilage callus is completely formed, ossification centers start reforming that cartilage into bone. And so a woven bone callus forms, which does not have any particular orientation to it. It's not hard in the places where it's supposed to be hard or hollow in the places where it's supposed to be hollow. It's just there. But at this point, you can put weight on the bone now. And in fact, you should, so that the bone knows where to strengthen the compact bone and where to hollow out the medullary cavity. So that concludes our discussion of skeletal physiology. Hope you've learned a lot, and I'll see you again next time.